a stateless web tier, shared cache, and master-slave database. At regional scale, this functions smoothly, but a surge of global traffic exposes physical constraints. Web servers hit memory ceilings, and database capacities are exhausted. At this scale, three specific choke points emerge. First, distant users experience high latency. Second, heavy background tasks gridlock servers. Third, databases run out of space. Resolving these limits requires moving away from simply purchasing larger and larger servers. The entire architecture must be decoupled so distinct functions can scale independently. To restore performance, we have to implement multi-data center routing, insert asynchronous message queues, construct a centralized telemetry system, and finally, shard the data tier. The monolithic design that successfully serves 100,000 localized users will completely buckle under the weight of 1 million distributed ones. Physical distance dictates network latency. If your single data center is located in US East, a user connecting from Asia must wait for packets to cross multiple oceanic cables, resulting in unacceptable ping times. To solve this, we mirror the entire infrastructure into a second physical data center on the opposite coast. A GeoDNS service intercepts user requests and maps the IP addresses based on location. It constantly calculates the shortest physical path, directing Asian traffic to US West, while European traffic routes to US East. Beyond speed, multiple data centers secure the system against physical destruction. Natural disasters or major power grid failures can take an entire regional facility offline. This diagram shows a failover scenario. When US West goes dark, the GeoDNS mechanism instantly redraws the routing map. It redirects 100% of the global traffic away from the dead zone and into the healthy US East data center. This redundancy introduces a severe data synchronization challenge. If a user's traffic is suddenly routed to a backup data center, their localized cache and database records must already be there, requiring complex, real-time asynchronous replication across oceans. Maintaining a flawless uptime illusion for a global user base requires engineering an edge layer that assumes physical hardware will inevitably be destroyed. Within those active data centers, the web servers face their own gridlock. When a user uploads a high-resolution photo and applies a complex crop and blur filter, the server executes those tasks synchronously. The server receives the file, processes the pixels, and waits to return the result. For those 10 seconds, that specific machine is held hostage, consuming vital memory and blocking new incoming requests. To eliminate this synchronous gridlock, we introduce an in-memory message queue. This acts as a durable, asynchronous buffer between the user-facing web tier and the back-end processors. The web servers act strictly as producers. When a SOTO upload arrives, the server instantly drops a processing job onto the queue, returns a success message to the user, and immediately frees itself to accept new traffic. On the other side, a dedicated fleet of back-end worker servers acts as consumers. They connect to the queue and pull down the heavy processing tasks, executing them systematically at their own pace. This decoupling absorbs massive traffic spikes. If a feature goes viral, the queue simply grows longer, buffering the shock. We can then scale up the worker pool horizontally to chew through the backlog without ever slowing down the primary web servers. By separating instantaneous user responses from heavy data customization, the system isolates high-intensity workloads from cascading into widespread web tier failures. As the infrastructure splinters into load balancers, message queues, and worker fleets, manual debugging becomes impossible. You cannot SSH into 1,000 isolated machines to locate the single server returning a 500 error. Operators require continuous streams of data, host-level metrics for CPU and memory, aggregated cache performance, and centralized database query logs. We solve this by building an observability layer. Specialized tools extract error logs and telemetry from every individual component and aggregate them into a unified health dashboard. Because this fleet is constantly expanding and contracting, manual code deployment is equally dangerous. Teams must implement continuous integration and automated deployment pipelines to verify and ship code across the data center simultaneously. At this scale, operational visibility must scale horizontally right alongside the architecture. Without precise metrics, resolving a failure across a decoupled system is guesswork. Even with optimized edge routing and asynchronous workers, the architecture eventually collides with the most rigid bottleneck of all, the master database running out of physical disk space. This illustration compares the two broad approaches for database growth. On the left is vertical scaling, adding raw compute power to a single machine. On the right is horizontal scaling, distributing the load across many servers. Vertical scaling has a strict ceiling. Procuring a server with 24 terabytes of RAM is astronomically expensive, and no single piece of hardware can hold infinite data. The solution is database sharding. This requires physically breaking the massive, monolithic database into smaller, easily managed parts called shards, each holding a unique slice of the total data. This flowchart displays a specific routing logic. To ensure data is distributed evenly and retrieved instantly, we apply a mathematical hash function, like calculating the user ID modulo 4, to act as the sharding key. This schematic maps specific user IDs directly into isolated database nodes. If the hash output equals 1, the query routes exclusively to shard 1. The application bypasses the massive monolith and reads only from the exact server holding that user's data. But this mathematical distribution creates the celebrity problem, also known as a hotspot key. If millions of followers simultaneously request data from a highly active account, all of those read operations are mathematically routed to the exact same shard. That specific database server becomes overwhelmed and melts down, while the other shards sit idle. Furthermore, once data is physically separated across different servers, executing a standard SQL join operation across tables becomes incredibly difficult. Engineers are forced to denormalize the data, duplicating it so queries can run within a single isolated shard. Sharding permanently shatters the physical hardware limit, but in exchange, it forces you to manage extreme routing complexity, uneven traffic distribution, and heavily fragmented data tables. We have successfully evolved the architecture. A single request now navigates GeoDNS routing, hits load balancers, deposits background tasks into message queues, and queries deeply sharded databases, all monitored by a centralized telemetry hub. Supporting millions of users is an endless cycle of continuous refinement. You locate the most stressed component, calculate its limits, and engineer a bypass. The governing principle is strict decoupling. Every tier of the application must be separated so it can buffer shock, scale out horizontally, and fail independently without dragging down the rest of the system. What starts as a simple script running on a single piece of hardware has to fracture, multiply, and coordinate across an entire continent. A centralized system will inevitably be crushed by global demand. Distributing the load across specialized, redundant networks is the only mechanism that ensures a system survives.